The topic of today's video lecture is Born-Oppenheimer approximation. So, in this video lecture, I am going to explain what really is Born-Oppenheimer approximation, the equation, and how does it change the Schrödinger wave equation, and how does it make it easy to solve the Schrödinger wave equation. Okay, so introduction. Well, if you consider a many-body system, that is a system that contains a number of electrons and nuclei. Okay, that is a many-body system is such a system in which there are many electrons and nuclei. So, in that case, Schrödinger wave equation becomes very much difficult to solve. Why does Schrödinger equation become difficult to solve? Because when there are a number of electrons and nuclei, when there are a bunch of electrons and nuclei, there are electronic repulsion, the electronic nuclei attraction, and the nuclei repulsion. Okay, so these are the factors that makes the Schrödinger wave equation very much difficult to solve. So the many-body system is too complicated to obtain the accurate result by solving the Schrödinger wave equation. So in a many-body system, the Schrödinger wave equation cannot give us the accurate results. Okay, so according to the Born-Oppenheimer approximation, the electrons are about 1800 times lighter than nuclei. Okay, you know this fact that electrons are 1800 times lighter in mass than the nuclei. Similarly, the motion of an electron is much faster as compared to a nucleus, because as you know that nucleus are heavy, the nuclei are heavy while the electrons are lighter. So electrons moves very fast, whereas the nuclei move very slowly. So this approximation divides the complex motion into two parts. Okay, Born-Oppenheimer approximation states that the motion of this many body system can be divided into two parts, that is the motion of the nuclei and the motion of electron. And you already know that the motion of nuclei is very small as compared to the motion of electron, because the electron are very light and can move very fast as compared to the nuclei. Okay, so the motion of a nucleus as compared to an electron is very slow and it can be neglected. So nuclei are considered to be fixed. Okay, because as you know that nuclei are very heavier, so they move very slowly. So we can say that nuclei are fixed as compared to the electrons because electrons are moving very fast. So that's the approximation of Born-Oppenheimer. Okay, so moving on, similarly, the kinetic energy of a nucleus can be neglected in Hamiltonian operator, because as you know that the Hamiltonian operator has a kinetic energy operator and a potential energy operator. Okay, so in the Hamiltonian operator, the kinetic energy of a nucleus can be neglected. Okay, how can you neglect the kinetic energy of a nucleus? Because as you already know that the nucleus has a very small motion, very low motion as compared to the electrons, and the kinetic energy depends upon the velocity. Okay, the kinetic energy depends upon the velocity, and you know that the nucleus has very much low velocity, so the kinetic energy of the nucleus can be neglected. Okay, so basically I can say in that in the Hamiltonian operator I can neglect the kinetic energy operator of the nucleus. Okay, so now Hamiltonian operator in its original form when divided into nuclear and electronic motion can be given as just like this. Okay, here as you can see that this H represents the Hamiltonian operator, this Te is the kinetic energy operator for the electron, Tn is the kinetic energy operator for the nucleus, Vn is the potential energy operator for nucleus repulsion, and VEE is the potential energy operator for electronic repulsion, and again VNE is the potential energy operator for attraction between the nucleus and the electron. If we plug in the values of all these operators, the Hamiltonian becomes okay. So now what you have to do, you just have to plug in the value of all these operators. Okay, first of all, the kinetic energy of the electron, the kinetic energy operator of the electron. So when you plug in the value of the kinetic energy operator of the electron, so if there are I electrons and m is the mass of the electron, so this here is the kinetic energy operator for the electron, and this here is the kinetic energy operator for the nucleus of mass m. Okay, and similarly this is the potential energy operator of the attraction between of the repulsion between nuclei between the both nuclei. Okay, the nucleus nucleus repulsion, the potential energy for the nucleus nucleus repulsion is given just like this, and similarly the potential energy operator between the repulsion of the electron is given just like this. And again, this term is the attraction, so as you know that for attraction we have changed the sign to negative. Okay, so for the attraction we have the attraction between the electron and nucleus, and the potential energy operator is given just like this. Okay, so now as you already know that I have explained you before that Born-Oppenheimer approximation separates the motion of the electron and the motion of the nucleus. So according to this approximation, the psi can also be divided into psi n, means wave function of the nucleus, and the wave function of the electron, means that the wave function, the total wave function, can be divided into two parts: the wave function of the nucleus and the wave function of the electrons. Okay, so now this r represents the coordinates of a nucleus, and this small r represents the coordinate of the electrons. Okay, so now the nuclei wave function can be neglected. Okay, so now as you know that the nuclear part of the Hamiltonian can be neglected, so Hamiltonian becomes equal to TE plus VEE and VNE. Here TE, as you know, that the kinetic energy operator, this is the potential energy operator for electron-electron repulsion, and this is the potential energy operator for the nuclear electronic attraction. Okay, so which terms we have neglected? We have neglected the Tn term, we have neglected the pure nucleus term for its kinetic energy operator, we have neglected the term, the potential energy operator for nucleus nucleus repulsion. Okay, and this term and this term is remaining in the Hamiltonian operator. Okay, so this is the Hamiltonian operator, the electronic Hamiltonian operator, in which we have only the kinetic energy of the electron, the potential energy operator of the electron electron repulsion, and again the potential energy operator for the nuclear electron attraction. Okay, so now what we have to do, we just have to plug in the values of each of this, and this equation becomes, this Hamiltonian becomes just like this. Okay, so as you can see here that the kinetic energy operator for the electron is given by just like this, the kinetic energy of I electrons of having a mass m, and similarly this is the electron electron repulsion term, and this is again the nucleus electron attraction term. Okay, so now the Schrodinger wave equation finally becomes He psi e is equal to E psi e. Okay, so that means that the Schrodinger wave equation, the Hamiltonian operator, contains only the electronic terms and the nucleus terms are neglected. So when the nuclear terms are neglected, the equation, the calculations become very much easy to solve. So that's why we just neglect the nucleus terms, the nuclear motion in the Hamiltonian operator, so that the Schrodinger wave equation become very easy to solve and we can get the accurate results. So that was all for today's video. If you have any question, you can ask me in the comments.